Okay, cool. So this is work on partial type constructors. It's joint work between Mark Jones, Richard Eisenberg, and myself. Before I get into that, I want to tell you a story about one of my friends. So this is my friend UArray. Like most of my social circle, it's a Haskell type constructor. And UArray is, okay, we're going to get along. UArray is one of a series of ways to build arrays in modern Haskell. So, you know, Haskell has a data type called array, and you can build something that's called like an array int double. And that first argument is about how we index into the arrays. It doesn't matter. It's going to be there the whole talk, but it will never matter. The second thing is the thing that you're finding in the array, doubles, right? And Haskell values are boxed. So, you know, when we say array int double, we get an array of boxes, and each box contains a double, as you would expect. Now, you know, C programmers might look at this and think that's not exactly what I mean by an array of doubles. What I mean by an array of doubles is a bunch of doubles in memory next to each other. Okay? And we can do that in modern Haskell as well, and that's where UArray steps in, right? So a UArray, or an unboxed array of doubles, looks like a bunch of doubles next to each other in memory. Okay? Now, GHC has support for unboxed types, right? They get funny names with hashes on the end of them. That's not what's going on here, right? This is the normal double type. It's I put normal doubles in there, 1.0, not 1.0 hash. But the compiler knows how to unbox a double, right? So it knows how to take the box double that I give it and fit it into this array that doesn't have any boxes. Okay? But on the other hand, there are a whole bunch of data types, the vast majority of them, that GHC doesn't know how to unbox, right? It doesn't know how to unbox integers. It doesn't know how to unbox int-to-int functions and so forth. So a type like UArray int-to-int or UArray int integer doesn't make much sense. GHC doesn't know how such a thing would work, right? And so the way that works now is that those types are effectively empty, right? They contain divergence because all types in Haskell contain divergence, but they don't contain anything else. The intuition I want you to keep in mind is that this is basically a partial type constructor. There are some type arguments, like int and double, for which this thing is well defined and it gives you back a type. There are other type arguments, like int-to-int and birthday cake, for which currently this gives you the empty type, but what I really want to say is that those aren't defined. They aren't meaningful, right? I'm not saying empty types in general are a bad thing. It's good to have a unit to sum. But sometimes we have these type expressions that we might write down that don't actually seem to be meaningful, and where the empty type seems like it might be a poor approximation of the actual meaning that we intend. So why do I say it's a poor approximation of the meaning, right? That's what we do now, and it seems to work. Well, let's think about how UArray gets along with the other list collection constructors in Haskell, right? So what can I do with a collection? Well, one thing I can do is I can map functions across it, right? So if I have a collection of integers, I want to make them all larger. I can do this with a +1 function. And so if I want to take a list of ints and make a list of slightly bigger ints, then I do that with a function called fmap, and it's very nice. And if I want to do this with an array of ints, and take an array of ints and make an array of slightly bigger ints, I can do this with a function called fmap, and it's very nice. And if I want to do this with a UArray of ints and get a UArray of slightly larger ints, I can do this with a function called amap, and it's very nice. Now, I had a subscription to highlights for children, and so I recognize when something's different from the rest of its friends. And in particular, the problem here is not that typing amap is hard, right? And it's not that remembering to type amap is necessarily hard. It's that I'd like to be able to abstract over these things, right? That's what's fun about Haskell, is that we can build these higher order abstractions that make programming easier. But this is breaking that higher order abstraction, right? I can write fmap +1, and that makes all kinds of collections of integers contain all kinds of collections of slightly larger integers, so long as they aren't UArray collections, right? So the idea is UArray is like a functor. It seems to have the bits of a functor, but it's not a functor. And this is not a story about how GHC is mean, because the thing is UArray is genuinely not a functor. Let's look at another thing I could map. So I might want to map from integral across lists, right? So I could map from integral across a list of ints and get a list of integers. I could map from integral across an array of ints and get an array of integers. In fact, one could imagine, if GHC let UArray into the functor club, that I could fmap from integral across a UArray of ints and get a UArray of integers. What would that mean, right? One of the things that fmap is supposed to do is preserve structure, right? If I fmap across a list of length 5, I get a list of length 5. If I fmap across an array with indices from 2 to 10, I get an array with indices from 2 to 10. And if I could do this fmap from integral across a UArray, I would start out with a UArray that might, say, have 8 integers in it, or 8 ints in it, and I would end up with divergence, right? And that's not the way fmap is supposed to behave. So this isn't a question, this isn't a matter of the compiler not being nice. UArray in Haskell as it is now is genuinely not a functor, right? Now, I think this is a problem, and I think it would be neat if UArray were a functor, and if we could fmap across it, and if we could figure out how to rule out fmapping from integral across a UArray. Many of you are at this point convinced that you don't care about this type. You will never care about UArray, and that I have poor choice in friends. And so when we got to about this point in the work, we said, well, how often does this really happen, right? How many partial type constructors are there out there? And so we went for a look. Now, so there are a bunch of collection types. I will mention binary search trees once more. I'm really not going to talk about the set monad problem. But you know, binary search trees are an example of something where we might want to assume ordering, and we might have trouble ordering int-to-int functions. But there are lots more, right? Haskell has a beautiful collection of numeric types, and they include numeric types that you can build out of other ones, right? Ratio and complex. You can build a ratio of ints, you can build a ratio of doubles, you can build a ratio of booleans, and that means something. You can build complex numbers where the complex part is character-to-character functions. I'm not quite sure what that means. We've got monad transformers, right? And the second argument to a monad transformer is a model of the underlying computation, right? So monad state int list int, you know, combines state and non-determinism, and monad state int ratio int combines state with There are type functions, right, which we can write. So we have a type function like elem that gets out the type of a collection, right? So elem list of t would give you back t. Elem array int t would give you back t. Elem bool would be a thing. There are various proposals. For example, unpointed types. The Launchbury-Patterson proposal ends up with a couple of different function types that aren't always defined all the time. So I think there are actually a number of these running around that might all become better, easier to use if we could better support partial type constructors. So what would it mean to embrace partiality, right? To say, you know what, maybe partial type constructors are cool. Maybe our language should support those. Well, the first thing we wanted to do is we wanted to see if anybody had done this already, right? You should look at the research. And so I want to tell you about a language called Haskell. I don't have a copy of the Haskell report from Glasgow in 1990, but one of my co-authors does, described it as the best £5 he spent as a graduate student. And so he was able to look through this definition of the language Haskell and see what exactly Haskell provides along the lines of support for data types. And if we look at this page here, there's a really cool paragraph. The main point about contexts above is they're given a typing, blah, blah. And there are these examples, right, of types and types synonyms and data types with contexts in them. And there's this statement, the context portion of these declarations declares that a type is only valid when the constraints hold. Right? So we can say that BST of A is valid exactly when OR of A holds. And that seems really nice, right? That's exactly the thing that I wanted. So why don't we do this? Right? Why isn't this a feature we want? Well, I also don't have an archive of the Haskell mailing list back to 1991, but Mark does. And so we find the following email from Simon Peyton Jones. Nobody has been able to give a satisfactory account of what contexts and data and type declarations actually mean. And so Simon proposes basically reducing them to what they are now. And so the other way you can view this talk is not about UArray and so forth and so on, but it's about picking up a challenge that was put down in 1990 of what should contexts in data and type declarations mean. So in contrast to the previous talk, I'm going to try to talk about nothing that was sort of valid after Haskell 98. The core challenge, as I see it, is to say, how do we know when a type is defined? Okay? So this first thing is, I've claimed good, right? We see, yeah. UArray int, we know how to build that. We know how it works. UArray int arrow int, we know that that's a bad thing, right? We know that GHC has some idea of what it can unbox, and we know that int is not one of those things that it can unbox, right? So far, so good. What about this last thing? What if I say for an arbitrary functor, is f of int well-defined, right? Well, if I want to allow partiality to my language, if I want to allow UArray to be a functor, then I don't know, right? We genuinely don't know whether f of int is going to be well-defined or not. Our solution is to say, well, maybe that's the idea that we need to capture. We need to capture exactly the idea of when it's possible to apply a type constructor to an argument giving a well-defined type. And we're going to do this with a predicate on types that I'm going to spell at. Basically, think of f at t as being a constraint that says this constraint is satisfied when type constructor f is applicable to type t. Okay? So we would expect that the constraint UArray int at int would be satisfiable, right? We could discharge that constraint. We can build UArrays of ints. We would expect that the constraint UArray int at int arrow int would be unsatisfiable, right? We should know that we can't unbox int arrow int things, and so we can reject this constraint immediately. For an arbitrary type A, we know that that type is well formed if and only if we could unbox A. Right? Now, GC doesn't have this constraint right now, but I could imagine an unboxable constraint, right? Which would be satisfiable exactly, U array int at A would be satisfiable exactly when A was unboxable. Okay? So we're trying to capture the cases where types can be undefined. One point I want to make is that this naturally extends to characterize total type constructors. Right? A total type constructor is one for which at's always satisfiable. Right? So we always expect that we can satisfy the constraint list at A. We always expect we can satisfy A arrow at B. Right? And so taking this sort of like, let's consider every type we're partial, doesn't rule out total type constructors at all. In fact, there's going to be a naturally degenerate case of a partial type constructor. Then we're going to insist that to be well-kinded, a type has to be well-defined. Okay? So at the beginning, we're going to say U array int int is a type. We're going to say U array int int arrow int is not a type. Right? This is where our proposal is actually diverging from the way Haskell is now. So we're not saying that's the surprise empty type. We're not saying it's sort of a special nothing. We're saying it's not well-kinded. Right? You don't get to talk about these types. And that means that when we have type variables, we're going to have to carry around constraints that make sure that their applications are well-defined. So the type functor f implies f of int is not well-kinded in our system because we don't know that f is applicable to int. But if we ask for that information as well, if we say we know that f is a functor and we know that f is defined at int, then the type f int is perfectly well-kinded. It has kind star. Right? Now, some of you may notice what seems to be a little bit of redundancy in this declaration, right? I have a type application, and then over on the left-hand side of the fat arrow, I have a statement that I better be able to do this type application. And I believe that is redundant, and I'll come back to that in a point. How do these things come about? Well, we'll just repurpose context and data declarations to do what they were always supposed to do, right? If you have a data declaration, ORD A implies BSTA, then we'll derive the rules for the at predicate from this. And I do have to point out this is not the same as a GADT, right? So for a GADT, we might say, well, the type BST int arrow int exists, but it's empty or it only contains some default value. Here we're saying that's genuinely not a type. You're not allowed to talk about it. Okay? Now, if I go back to that thing where I said some of this information seems to be extraneous, in a lot of cases, we can infer these definedness constraints from the structure of types. Okay? So this is the functor class. And this is the form that it would look, this is the sort of type that we would give fmap with definedness constraints so far. Okay. So we'd say, you know, if you know that you can apply f to A, you know that you can apply f to B, then functor has this type. And in fact, we've already simplified a bunch of constraints about arrows that we know hold. But what I argue is that we can automatically elaborate type applications that the programmer writes down to add in these definedness constraints. I'm going to assume that when the programmer writes FA, they genuinely intend F to be applied to A. And so if I do that, I'm going to erase these constraints that I can automatically elaborate and just give functor this type here. And the cool thing about that is that if I don't change the apparent definition of functor, that also means I don't have to change any of its uses. But what I can do now is make things like UArray an instance of functor because the bad cases, the cases before that broke the functor laws, are now simply ill-kinded. Right? We're not allowed to talk about them at all, so we don't have to worry about whether or not they've broken the laws. But this doesn't mean that every at constraint goes away. If I imagine implementing sort in terms of BST, there's no reference to BST in the final type of sort, so you might imagine you still have to quantify over BST at A. But here's the thing. That's just ORD A. And you already needed to write that for the type of sort. Okay? So what's in the paper that I haven't told you about? Well, there's a bunch of formalization. In particular, there's an intermediate language without partial type constructors. But what it does have is evidence in types. So when you talk about a type like BST, that can actually carry around the ORD dictionary for A. We have a type-preserving translation from our surface language to that intermediate language, right? So we're not proposing a grand new meaning of data types. We're proposing a nice interpretation of data types that we can map to our existing meanings. And we also took a sample of Haskell code. We'll call it the Hughes prelude. And we checked to see how many definedness constraints we would actually need to add by instrumenting Hughes and compiling the prelude. And we discovered, I say minimal annotation overhead, there were 4 functions, right? And in 3 of the cases, there was a very simple change actually to the way the function itself was written that made the need for a definedness constraint go away. Now, some of you will think that this feels familiar, right? Some of you are named John Hughes. And in fact, there have been a number of proposals along this line that have come before, and I want to sort of, in the time that I have left, mention a few of them. So this is very strongly inspired by Hughes restricted data types. There are two forms of restricted data types in that paper. I've written up here the second. In that second one, there's a need for these explicit context arguments in class declarations. And one of the things that we wanted to do is to, as much as possible, keep the meaning of existing code and to put the burden on the partial data type, not on everyone who's using it. Right? So we don't want to have to write a new functor class that specially accounts for partial data types. We want partial data types to account for themselves when they get to the existing functor definition. Orchard and Shrivers came up with a sort of very nice extension that realizes Hughes' thing. Our approach is really just sort of a generalization of that. It's also worth pointing out that these things can happen in bounded polymorphism. Or this can look very similar to bounded polymorphism. There are a couple of differences between our approach. One is just the natural trade-off of subtyping versus qualified types and inference. The other difference between what we're doing and what's turning up in Scala is that we really want to make these at constraints implicit as much as possible. And the argument there is that they should be explicit. I think that's a language design question, but it is a difference between the two approaches. Well, that's what I have to say. So I'd be happy to take any questions.
So I don't see any questions on Slido yet, so anyone in the audience?
There's one at the back.
Someone in the back?
Hi, thank you a lot for your talk. It was very interesting. So I have some questions around the functor example. So for one, it seems that the example that you have towards the end where you have the additional constraints, and so for example, you can't have, int to integer mapping uArray int to uArray integer. It seems that that's no longer a functor because functors say that, if we have a function from type to type, that we should be able to map it into something else. And it seems that you've modified functor into something that is less general than an arbitrary functor, and that for an arbitrary functor, you would actually be able to have this preservation. So if you could account for that a little bit, I'd be...
So there are two things I can say to that. One is to say, our starting point is that we think partial type constructors are cool. So think of this as a language design that takes that as the default assumption. And so under that assumption, the way we want to interpret the default definition of functor is as one that extends to partial type constructors. So, when I write this type FA to FB, that type implicitly requires that FA and FB are defined. Now, it's perfectly possible without any of, you don't need anything else to add to the system to be able to capture totality, right? And you can have a very nice constraint alias or something that, total of A or total of F is equivalent to the constraint for all B, F at B, right? So if you really wanted to say, no, I mean exactly total type constructors, we can do that. I think if you found that particularly useful, that would indicate somehow that our mechanism wasn't working. I think if you found yourself really needing to say my program doesn't work unless I know that this thing is total, that indicates that we're not supporting partial type constructors as well as we'd like to. So you can do it. I just hope you wouldn't want to. There's another question over here before we. No?
Thank you for resurrecting the context in data type declarations so that you could constrain something by a type class from Haskell 1.0. I had never, it's nice to know sort of that I was right, but also I'd never understood this idea that you need this at constraint. So it's very nice to see that brought out. It hadn't occurred to me at all. How long until we might actually see this go, until we can see Haskell go back to Haskell 1.0 where it belongs?
You were asking the wrong co-author on this paper. So the correct answer is to defer to my colleague in Cambridge. I would say I think that there's a complicated question, particularly if you, as I would try to do, push this work onto sort of core GHC developers about what's the right order to deal with sort of extensions to GHC. And so long as dependent Haskell or dependent GHC is a sort of looming thing, I don't know that we know exactly what the best way to add this to GHC would be. But I'm arguing for it. I will say I tried really hard to convince Mark to release partial hugs and to extend hugs to that. And apparently he found the prospect of resurrecting 1990s Lisp C code to be not as appealing as I thought it would be.
So you gave two examples of places where, sort of in principle, you need this constraint that like this type is applicable to this argument, but actually you could infer it, so you didn't need to write it.
Yeah.
Are there any examples in practice where you still actually need to write it?
So like I said, when we pushed the hugs prelude through our modified hugs, we found 4. 3 of them had to do with sort of clever ways to write functions that you didn't need to use. So map and unzip M, you can write either as a fold or as a concatenation over an intermediate list whose type doesn't escape. So if you just write it as a fold instead of as in a point-free style, then you get the type you want. We had one example of a function for which we could find no uses in the Hughes arrow library, a function called leftApp, whose type went a bit wonky, and where we did have really a bunch of intermediate types that didn't turn up in the input or output of the thing. But so they exist. I didn't find any of the examples we found terribly compelling. But
Okay, so that's all we have time for. So while the speakers switch microphones, let me introduce Sebastian Wolf from TU Braunschweig. I hope I pronounced that